game. It's application time here on All the Math. That's all the math you need for computer science. In this final episode of the volume, we are going to be talking about some eigenvalue applications, 3 of them, at least a couple of which you use every day. And we're going to start today by talking about video compression and how that is used in order to reduce the amount of data that must be streamed over the internet when you're watching Netflix or Amazon Prime or whatever, right? So fascinating thing, and all of these applications, including this one, have eigenvalues and eigenvectors at their center, okay? So we're going to see kind of the practical implications of why those work and how those work. Let me start by talking about the notion of information and what information something contains, or how much information something contains. All right, so here is an example of a haiku that I have composed. And this is using the form of the haiku that Mrs. Rieger taught us in 3rd grade. Or was it Mrs. Seastone in 4th grade? I'm going to have to fact check that. Anyway, the haiku is actually a complex Japanese form, but the one that's commonly taught to grade school students here in the US is the one where it's 5 syllables, 7 syllables, 5 syllables on 3 separate lines. Okay, so I think you'll agree if you count it out that this one satisfies the definition of a haiku, and I'm sure you'll agree it's very deep. Now, I want you to compare that with this haiku, which I'm going to claim also satisfies the form, and just take a moment to bask in the profundity of that second haiku. Now, let's talk about the difference between these 2 haikus. Clearly, they both have 17 syllables because we have decided that is the definition of a haiku for our 3rd or 4th grade American purposes. But they have different amounts of information in them, I'm going to claim. Okay, now you might say, well, how can they have different amounts of information if each one of them has 17 syllables? That's exactly the same amount. Well, the deal is that one of them is much more compressible than the other one. So if I looked at this first haiku and I said, wow, that's really cool, I want to tell my friend this, I would have to send them all 17 syllables in order for them to know what the haiku is. The second one, though, if I wanted to send that to a friend who I thought, really would appreciate this deep philosophy here, all I would need to say is blah 17. Right? I could say, hey, this haiku contains the word blah 17 consecutive times. So I actually don't need to waste my breath pronouncing the word blah 17 times. I can simply tell you what the word is and then how many times that word appears. And I've got all of the information communicated. Okay? In case you doubt that, here's a way to cement in your mind how the second haiku has less information in it than the first one does. I'm going to take them away. And I'm going to ask you right now, from memory, to write down those 2 haikus you just looked at. And I will bet that you find it way, way easier to do it with the second haiku. Not because you saw it more recently, but because it's just easier to memorize. Why? Because it has less information in it. You could right now just write blah 17 times, etc. That first one, though, I bet you remember some stuff, but you probably get a couple of the words wrong or in the wrong order or whatever, simply because it contains more information. Okay? Now, what does this have to do with video compression? Let's talk about the information in a matrix. Here is a matrix, M1, it's 7 by 7. And I want you to kind of fantasize here with me. What if you wanted to send this matrix to a friend? You wanted to send it to him over the internet. How many numbers would you have to include to send it? To do the math, you'll realize you'll have to send him 49 numbers, right? A 7 by 7 matrix has 49 entries. I'm sure you learned that since grade school, okay? So this matrix has 49 pieces of information you'd have to communicate, okay? Now, let's take a look at this matrix, M2, also 7 by 7. And I ask you, how much would you have to say over the internet to your friend who you wanted to communicate this matrix to? If you said 49 entries again, because it's 7 by 7 again, look at it again. For instance, let's look at the first column and compare it visually to the second column, and you'll realize, holy Moses, those are exactly the same. In both cases, it's 5, 3, 13, -4, etc. So these first 2 columns are exact duplicates of each other. Look at the third column, and with a little bit of squinting, you'll realize, oh, that third column is exactly double the first column. So the second column is a duplicate of the first. The third column is twice the first. Let's look at the fourth column. Whoa, that is exactly negative the first column. And the pattern continues. This column right here is exactly 4 times the first column. This penultimate column here, the sixth on the screen, is exactly 100 times the first one. And this last column here is exactly half of the first one, okay? So in terms of the haikus, we have the same sort of thing going on here, right? We don't actually have to speak 49 separate entries. As long as the recipient can expect the pattern, as long as the recipient knows, you're going to be able to give it to me in this form, we're going to be able to do the following. First, let's send them the first column. Okay, we can't avoid that, as it turns out. We're going to tell our person on the internet 5, 3, 13, negative 4, negative 21, 31, 6. Okay, so we told them 7 things. But now, instead of repeating that, what we're going to do is we're going to tell them what the multiplier is for each of the columns. So this is the first column, and we're going to say we want 1 of the first column, and then we want 1 of the first column, and then we want 2 of the first column, and then we want negative the first column, and then 4, and then 100, and then a half. So this vector right here tells you how many of the first column you want in each column location. Now, the astute listener will realize, hey, you know what? We could actually send this not in 14 numbers, but in 13, because you'll realize this one right here actually turns out to be superfluous, right? We know that the first one will have a multiplier of 1 because we gave it to them. So yes, you're very smart. Turns out that makes things a little bit more complicated to deal with that. So we're just going to say, let's send them 14 numbers, and they will know how to assemble the matrix from that. How are they going to do it? Well, this is actually the outer product, if you remember how that works. If you take 2 vectors, and you take their inner product, remember, that's the dot product, which just comes out to be a single number. You multiply each pair of entries times the other one, and then you add them all up, and that gives you the inner product. The outer product is when you make the first one a column and the second one a row, and you actually get this ginormous thing here, right? If you take a 7 by 1 times a 1 by 7, you end up getting a 7 by 7. However, you can see that the 7 by 7 is a little deceiving. It's brittle, is the way I think of it. Okay. Yes, it does have 7 times 7 entries. It has 49 entries, but they're really not all there in the sense that we can compress this into its components here. Okay. So the way I think about it is, if you only take 14 different numbers and you put them into an outer product, you're going to generate a lot of fluff. This whole thing is sort of like a big marshmallow that's just ready to be compressed, because it was assembled from these 2 smaller components in a regular way, okay? And so again, you're only going to need 14 numbers instead of 49, actually 13 if you're smart. Now, you might think 14 numbers instead of 49, is that really that big a deal? Well, with a 7 by 7, maybe 14 versus 49 doesn't seem like that big a deal, although we are shaving off, 3/4 of it or whatever. But this phenomenon gets bigger and bigger as we get a larger matrix, right? Because the number of entries in the full matrix is the square of the length of the side. Whereas the amount we have to send to do this outer product trick is simply the sum of the 2 sides, right? So if we have a 1,000 by 1,000 matrix, if we send the full thing, that's 1,000,000 entries. But we can get away with 2,000 entries if we just send the first column and then the multiplier of the other ones. Okay, so that's a tremendous savings. 2,000 versus 1,000,000, right? That's less than 1% of what it was. And it turns out that that's going to be the key to our video compression here. Okay, so here's some terminology for you. And actually, this is review, but it's good review. M1, that first matrix we saw, which was just the big crazy one with no pattern to it, that is called a full rank matrix. And you'll remember what that means is it has all linearly independent columns. In terms of our domino thing, this has been the song and dance this entire volume. It has got all yellow dominoes for its columns. M2, on the other hand, is a rank 1 matrix, which means it has hardly anything in it at all, even though it looks big, okay? And again, that means that there's only 1 linearly independent column. And we saw that, right? You have the first column, and everything else was just some duplicate of it, right? Some multiple of it. And so it contains less information. And that's conceptually what I want you to see, is that something that has less information is able to be compressible, just like the blah times 17 was, right? Now, these are the extremes here, okay? We have a full rank matrix, M1, and we have a plain old rank 1 matrix for M2. In general, of course, low rank does not necessarily mean all the way to rank 1. It can have any rank, okay? And that simply refers to how many linearly independent rows and columns that it has. And this whole thing is sort of on a continuum. The lower the rank of the matrix, essentially the less information it contains, and therefore the less we have to say to communicate what it is. All right? Now, what does this have to do with video compression? Well, imagine a frame of a video that you're watching. Imagine your favorite show, okay? And you're watching it, streaming it on Netflix or whatever, okay? So frames are whizzing by at 30 frames a second, or even more if you're watching it in high def, right? Every single one of those frames could be considered a matrix where the pixel has a certain intensity, or if you're watching in color, which most of us are, a certain red, green, and blue intensity, right? Now, the details of exactly how to represent graphical stuff in a matrix is beyond this course. And I will also say that I'm going to be simplifying a lot of stuff when I talk about this video compression thing, all right? And people who know about video compression will say, oh, yes, but you forgot this and that. Okay, yes, it's true. But nevertheless, the core idea, a big part of what it means to compress a video, which, by the way, just means use less space to store it and consume less bandwidth on the internet to send it, right? That's what we mean by compressing it. We mean sending you fewer bytes so that we're not taking up as much of your network stream, so that we don't have to store as many bytes on disk, right? We're trying to communicate essentially the same thing as your favorite Game of Thrones episodes or Breaking Bad episodes or whatever it is, with sending you fewer bytes, right? Okay, so if you imagine watching one of your videos, right, one of those frames is going to be up there for a 30th of a second, say. What we want to do is say, do we actually have to send all of those bytes individually? In other words, do we have to say for every single pixel communicate separately, independently, the red, green, and blue value? Or if you're using grayscale, which is what we're going to use here because it's just a little bit simpler, we're going to say that every pixel has essentially a number from 0 to 255 is what they usually use, where 0 means completely black, 255 means completely white, and in between is the in-between numbers, right? So we want to find out, is there a way to send that frame so that it looks pretty much like the original, but consumes far less amount of information? And the answer, of course, is yes, we can. And what we want to do here is we want to find a low-rank approximation to a matrix. That's what this whole thing is going to be about, low-rank approximations. And you can tell just from the sound what that is, right? It is a matrix which is kind of sort of close to the original one, and yet it takes less space. So let's just make this concrete. Let's say one frame of your video is 1920 by 1920 pixels, okay? Now, I know what you're thinking. You're thinking, wait a minute, that's a square, and when I watch a video, it's usually a rectangle because it's usually wider than it is tall, okay? Yes, that's true. The reason we're making it square here is it just makes the math a little bit easier and allows us to use eigenvalues. Here's a little tip for you. If you do end up using a rectangle instead of a square matrix, you can do exactly the same thing we're doing in this episode using a very, very closely related technique called singular values and singular vectors instead of eigenvalues and eigenvectors. So eigenvalues and eigenvectors go with square matrices, okay? And singular values and singular vectors go with rectangle matrices. That's one way to think about it, okay? All right, now if you crunch the math on this, you'll realize that's 3.6 million pixels, okay? That's a lot of pixels to send you for 1/30th of a second. Let's say we're doing it in grayscale, so each pixel is going to be like a byte, right? And a byte can hold up to 256 different values, as you'll remember from All the Math Volume 1. So the question we want to ask is, instead of sending all 3.6 million numbers for this 1/30th of a second frame, can we send a low-rank approximation to this matrix that we send instead? Okay. Now let me take you back to the spectral theorem from the last episode. You will recall that if A is a square vector, this right here is an equal sign. We're going to be making it an approximately equal sign in a moment, but right now it's an equal sign, which means A can be precisely broken down into these three components. And those three components are the eigenvectors, the eigenvalues in a diagonal matrix, which is otherwise zeros, and then the eigenvectors again, we have to invert that matrix. So if you have a matrix that has all the eigenvectors as columns, and you have a diagonal matrix of the eigenvalues, each of which are in order, each one goes with the corresponding eigenvector, and then you have the inverse of the eigenvectors, the spectral theorem says that will be equal, okay? Now, let's use an example here. I'm not going to use 1920 by 1920 because there's not enough room on the screen for that. Let's just take a 5 by 5 matrix here for a second, okay? And I'm always going to put this in blue to kind of help you identify it. This is the actual frame of video, say, that we want to send, okay? This is the truth. This is the real video. We know from the spectral theorem that I just showed you that you can break it down this way. It's going to have 5 eigenvectors. Why? Because it's a 5 by 5 matrix. It's going to have 5 eigenvalues. Why? Because it's a 5 by 5 matrix. Okay? So we're going to take the eigenvectors in columns times the diagonal matrix of the eigenvalues times the inverse of the eigenvectors. And if you actually crunch the numbers on that, I promise you this is what Python tells us are the eigenvalues and the eigenvectors. And if you multiply all this out, lo and behold, you will get back exactly the blue matrix. Okay, so that's old news. That is the spectral theorem in action. Now here's the magic. It turns out that to get a low rank approximation, something that's pretty darn close to what the original matrix was but takes a lot less space, all you do is, wait for it, take some of the eigenvectors, but not all of them. And the number of them you take is a trade-off between how much space it's going to take and how accurate the representation is. So if we say we only want to use the first 2 eigenvectors and the first 2 eigenvalues, we're going to get a very, very small amount of data that we have to transmit. The approximation won't be quite as good, though, as if we use 3 or if we use 4. And of course, if we use all 5, we get the exact answer. Okay? So again, let's just kind of look at this here. The best rank 5 or rank 3 or rank 17 or whatever approximation to a matrix is what you get when you use the spectral theorem and you only use the top 5 or top 3 or top 17 eigenvectors. Okay? Now, you might ask, what does best mean? You know, how do I know if it's the best approximation? Again, this is a complicated subject, and really in video, you know, there are certain things that your eye is drawn to, like the parts that are moving or the faces or whatever, and there are parts where your eye is not drawn to, and so, you know, sophisticated state-of-the-art video techniques try to compress more fully the parts that you're not really looking that closely at anyway, etc., right? Okay, so we're doing sort of a basic thing here. Our basic thing is we're just going to say, is the entire matrix, all parts being considered equal, close to the original one that you're trying to send? And what we're going to say that means is sort of the obvious thing. Just like we said, if we want to know how close 2 vectors are, we can compute the norm of their difference, right? We can subtract one vector from the other and then take the norm, which essentially like squares the distance between each point, right? It's essentially using the Pythagorean theorem, the sum of the squares of the differences for each coordinate. We're going to do exactly the same thing with a matrix. We're going to say, hey, if I have a 5 by 5 matrix and I have another 5 by 5 matrix, the way I know how good a fit it is or how good that approximation is I'm going to take each entry and subtract it from the corresponding entry in the approximation, square all those differences, add them up, and that's going to be what I call the distance between the 2 matrices. And by the way, the name for this is really cool. It's called the Frobenius norm. Okay, the Frobenius norm of a matrix is where you simply take the sum of the squared values of all of its elements. Okay, I always thought it was kind of a cool name. It sounded like a character from Willy Wonka and the Chocolate Factory. I could imagine, you know, somebody coming out and saying, "Hello, I'm Frobenius norm," or whatever. But anyway, that's what we're going to use here, right? All right. So let's say we want a rank 1 approximation. Okay, so we want the most brittle, marshmallowy 1920 by 1920 thing, or I guess in this case it's going to be 5 by 5. All we're going to do is say, let's take the dominant eigenvector, which is the one with the highest eigenvalue. Let's just take it and compute its outer product. Okay, so we've got the eigenvector here times the transpose of the eigenvector here. So this is just the outer product, and we're just going to stick the eigenvalue in the middle, because this right here is, if you think about it, a diagonal matrix of the one and only eigenvalue, right? I just put it there in matrix by itself because we only have one. And if you multiply all that out, this is the dominant eigenvector, and this is the dominant eigenvector transpose, and this is the dominant eigenvalue as we saw before. If you multiply that all out, you get this black matrix right here. Now I've put the blue one here, which again is our ground truth, just for comparison. And if you run your eyeballs over it, you'll see, you know, this really isn't that great. I mean, let's just take the top row. The true top row was 12, 2, 1, 9, 13. What we got from our approximation was like 8 and then 9. Ugh. and then 4.5, and then 7, and then 9. I mean, it's like not even really very good. And if you look at the Frobenius norm, if you add up the squares of the differences between 12 and 7.96, and the difference between 2 and 9.28, and the difference between 1 and 4.44, etc., add all those differences up and square them, you get 573. Now, that's just kind of a number. It's not obvious that that's high, but we're going to see that we can, of course, do a lot better. Let's talk about the best rank 2 approximation. So here's where I say, I'm going to go ahead and use 2 eigenvectors, the top 2, the ones with the highest eigenvalues. And this is what I get. So here's the equation, right? We're going to take a matrix with just the top 2. So this matrix right here is 5 by 2, right? Because the eigenvectors are 5 long, but we've only got 2 of them. Multiplying that by our diagonal matrix with just the top 2 eigenvalues. And then multiply that by a 2 by 5, because we're going to end up taking the inverse here. Now, the inverse is a little weird for a non-square matrix, but we're going to do this, this trick to it that essentially comes up with the pseudo-inverse, so to speak. And when you multiply all these things together, this is what you get, this black matrix. Now, I want you to run your eyeballs over this black matrix and compare it to the blue one. And I think you'll see, wow, that is like way better, right? Look at this. Instead of 12, we have 12.5. Instead of 2, we got 2.7. Instead of 1, we got 0. Instead of 9, we got just a smidge over 9. Instead of 13, we got 12 and some change, right? This thing is actually real close to the original matrix. And the Frobenius norm is 101 and change. Let's go with 3. What if we want to use the best rank 3 approximation? Well, we would take the top 3 eigenvectors and the top 3 eigenvalues, put it all through the machine. Out comes the sauce, and if we compare this black matrix to this one, we will see, it's kind of hard to eyeball and tell that this one's better, but I assure you it is. The Frobenius norm is about half what that other one is. So you can see sort of the picture here, right? Every time we add another eigenvector, we are getting a better and better approximation. That comes at a cost, because that's additional information we have to send. But what's going to turn out to be true is that the first small quantity of eigenvectors actually get us really close to the original image. And we're going to be able to send far less than half the data and get a really good illustration of what the image is going to turn out to be. Okay. In fact, let's look at this as an actual example, right? So let's say we have an 1800 by 1800 image. Okay. If you work out the math, this takes 3 megabytes if we wanted to send the entire thing. Okay. So this is one frame of a movie that you're watching. It would take 3 megabytes. What we want to ask is, how much would we have to include? How many eigenvectors would we have to throw into the soup before you, as a reader or as a viewer, can tell what it is? So actually, let's do a little example here, right? Here's the best rank 1 approximation to this actual image I have, right? So take a look at that for a second, see if you can figure out what it is. And I'll bet you can't. You might be using some meta information about what things Stephen likes to kind of help you with the clue. But without that, I think you'll agree it's kind of pretty much just black and white gibberish here, right? This has the virtue of being unbelievably small, right? So this only takes 3,000 bytes, right? Instead of 3 million. That's about 0.1% of the original, okay? So if we were actually satisfied with this and said, oh, this is close enough to send to the person, we could do this in almost no data at all. Now, let's add another one to it. Here's adding another eigenvector. Now, this is what the image looks like, and this takes twice as many bytes. Now, I want you to see if you can figure out at what point you can identify the image. Here's the best rank 3, best rank 4, best rank 5, 6, 7, I bet some of you have got it now, 8, 9, 10, 11, we've just passed about the 1% mark, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right? So every time we add another eigenvector, it becomes a little bit more in focus. And right now, probably everyone can see, this is, a character from Star Wars. And this right here is 2.4% of the amount of data we would have to send if we were sending the entire image without any compression, which, by the way, looks like this. Okay, so this is the original image. And by the way, you can tell maybe that I've chosen deliberately a difficult one here. This one's difficult to compress. And the reason for that is we've got some solid black areas right next to some solid white areas. And that turns out to be the most difficult thing to compress. If it's kind of more just a blurry shade of gray, it's a lot easier to get closer to it as the eye looks at it, right? But an 1800 by 1800 matrix has, of course, 1800 eigenvectors. Here's a way to get using only 22 of them, right? 22 out of 1800, and we're able to get this much of the information. And the reason for that, here's kind of this last diagram I want to show you. This is kind of showing the diminishing returns you get. So what I've got here is a plot, and on the bottom I'm showing the rank of our approximation, right? So we started with the rank 1 approximation, which was just, black and white gibberish. It looked kind of like a checkerboard more than anything else. And then all the way here, we could make this plot go all the way out to 1800 if we wanted, because the full matrix of that stormtrooper was in fact 1800 rank, right? Because it's 1800 by 1800 and it was full rank. And then what I'm plotting here is the error, right? The error in the Frobenius norm. So the error is gigantic at first. This is why you couldn't even tell what it is. With that first one, you didn't even know if you were watching the Disney Channel or HBO or whatever, right? But then, as you add eigenvectors, man, that norm shoots down. And if you only give the first 30-ish or so, you've gotten the lion's share of the image. And everything else after that is just making it that much crisper and that much crisper and that much more accurate. And again, this is kind of interesting how you can tune it, right? And I'm sure you've watched video, on YouTube or on Amazon Prime, and sometimes you can pay more for it to get the high definition one instead of the standard definition one, right? Essentially what they're doing, and again, I'm glossing over some details, but essentially what they're doing is dialing up how many eigenvectors they use, right? And if they are sending you more data, they'll charge you more for that, but you are going to get a more high-res image, okay? But again, since these frames are zipping by at 30 per second, that's why the movie watching experience is pretty tolerant of not exactly being accurate to what, a high-res, high-definition photo still would be. Because the human eye can't tell all those different things anyway, and it's just going by so fast that you're paying attention to more than just, wow, is every single edge correct on that? Okay? So anyway, here's a very practical application of eigenvectors and eigenvalues. And again, it shows how those show the deep structure of the matrix. The first few eigenvectors that have a really high eigenvalue contain almost all of the information. And so if you just pick out those first few and kind of hit the sweet spot before the diminishing returns come, your eigenvalues have really saved the day.